Hello, Physics Nation. My name is Nate Larmond, and I'd like to do another physics craft, another cardboard pulley. Here is the original cardboard pulley. This thing is called Atwood's machine. We made a little, we made a little hamburger out of cardboard, so the outside diameters are just a little bit bigger than the two inside diameters. Glue it up, tape them up, and like I said, you can hang the two weights off of the pulley and examine the relationship between the total mass of the system, the net force, and the acceleration. So, counterclockwise, that is a positive z rotation. That's coming at you. The penny, however, is rotating this thing clockwise. So that's a negative z. So I think I may have gotten carried away with the mathematical details for the first pulley lab. We're using coins as mass standards. So, we had to change 2.5 grams into kilos. You divide by 1,000 grams per 1 kilo. And, you add up the two masses. So there's the total mass of the system. Then you had to find the net force. Well, 1 kilo weighs about 10 newtons. And so we had to figure out who was winning this little tug of war. Over here we have a heavy force, and over here we have a light force, or a smaller force. And so the net force is the difference of these two weights in newtons. Again, 1 kilo weighs about 10 newtons. And then we wanted to describe the motion, the acceleration. So we measured distance and time, divided those to find the average velocity, double that to find the final velocity, and then we found the rate of change of motion, the acceleration of this system. So the elevator was not in balance. This is not equilibrium because it's accelerating. For this next lab, I want the system to be in balance. I want to achieve equilibrium. So what does that look like? Well, I haven't quite figured out how the assignment's going to look, but this is the apparatus. We've got a hanging weight that's over here. I have 2 pennies and a quarter hanging off my pulley. And then you need a sled, a weight that gets dragged. So like I said, we're trying to achieve equilibrium, that is no acceleration. So right now, when I let go, the system is not in equilibrium. It's accelerating because the tension provided by the hanging weight and redirected by the pulley, that's the whole point of pulley systems, to redirect forces, is greater than the backwards force pulling on this sled. So we've got a little horizontal tug of war. Tension pulls it forwards, and friction pulls it backwards. So what we're going to do is we're going to change the friction force in between my little sled and, well, it's an instrument case. I just wanted something smooth. This is nice, even plastic surface. Like I said, we're going to try to increase the friction force. And how are we going to do that? Well, we're going to put money in here. All right. So we don't have our normal mass standards. We're just using quarters. 1, 2, 3, 4, 5, 6. Let's try 6 quarters. Oh, still accelerating. That's pretty close, honestly. So tension, this weight is still greater than the backwards force of friction. Let's add 7 quarters. Now have we achieved equilibrium? This is actually pretty close. I want this thing to move at a constant velocity. How about 8 quarters? And I think it's there. So what we're trying to do is we're trying to figure out how much weight does this thing need to make the friction force equal to the hanging weight. And then we're going to compare these two forces with a ratio. It's called the coefficient of friction. And it looks complicated. It's not. All you do is friction divided by normal force. So in this case, the hanging weight divided by the sled's weight will provide the coefficient of friction. Happy crafting. See you in the next video.